Welcome to the Problems Channel Season 2, Episode 43, the episode which I titled A Poisson Integral by the Book, because in this episode we will evaluate a certain definite Riemann integral that is usually associated with the name of a French mathematician, Simeon Poisson, who lived between the years of 1781 and 1840 by the book, or using precisely the divide and conquer problem solving approach. Before we do that, however, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for subscribing to our channel. Welcome to our channel. And second of all, it is a good idea for you to go to the homepage of this channel and in the channel's trailer section, find the episode titled The Problems Channel How To. Watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. In the mathematical problem S2E43, which I marked with an asterisk for the reasons that will become evident as this episode unfolds, we're asked to use precisely the divide and conquer problem solving approach in order to evaluate a certain definite Riemann integral that is usually associated with the name of a French mathematician, Simeon Poisson, who lived between the years of 1781 and 1840. And the structure of the integrand of this integral is the following. We're asked to evaluate a definite Riemann integral between the boundaries of 0 and pi of the natural logarithm. This is the sign over here for the logarithm in base e. And the argument to this logarithm in base e is the following: 1 minus 2 times a real number r times the trigonometric function of cosine evaluated at the argument x plus r squared. And this is the end of the argument to the logarithmic function, and the integration is carried out with respect to the variable x, not r but x, and the cosine of x. This is where all the action unfolds. We're also not told anything about the quality of the real number r, and the burden to analyze how different possible values or ranges of values of the real number r affect the value of this definite Riemann integral is on us. For example, one thing we can see right away, that when r is equal to 0, then the last summand r squared becomes 0, the middle summand becomes 0, the only non-zero summand becomes 1, the logarithm of 1 is a constant real number, it is 0, and it is one of the fundamental properties of the definite Riemann integrals that an integral of a constant is equal to the constant times the value of the integral. In this case, the value of the integral from 0 to pi is pi, 0 times pi is 0, so evidently we can say, for example, right away, analyze that the case when r equals to 0 is not interesting. Consequently, we will consider the cases when the value of the real number r is not 0. And the interesting question is, how exactly does the divide and conquer problem solving approach dovetail into the process of evaluation of this here definite Riemann integral? By now, those of our viewers who tag along and pay attention should know the description of the divide and conquer template by heart. That is, if we want to apply the divide and conquer problem solving approach to the process of generating a solution of a technical problem, then we should try to carry out the following 3 steps. First, we want to identify a whole, and then we want to divide that whole into a number of smaller and simpler primitive parts. 2, we want to pedantically and just in case generate all the solutions of all the smaller and simpler primitive parts. And number 3, we want to find a way to combine all the solutions of all the smaller and simpler primitive parts into a solution of the whole. As such, in this specific problem, what is the whole? In this particular problem, the whole will be the area of the planar region that is trapped above the x-axis, below the graph of the given function that is being integrated, and between the vertical straight lines x equals a and x equals b, shown over here, b on the right, a on the left. Once that major discovery, if you will, is made, and the discovery amounts to the observation that numerically the value of the definite Riemann integral shown over here from a to b of the function f of x over the variable x is equal to the area of the planar region that I just described. Once that discovery is made, we can extend that idea, but that extension to the situations where the function on the integration interval is negative requires the introduction of the so-called signed areas. In other words, the area of the planar region that is trapped above the x-axis and below the graph of the given function that is positive on the interval a and b between the vertical straight lines x equals a and x equals b is associated. The plus sign is taken to be positive, and the area of the planar region that is trapped below the x-axis and above the graph of the given function f of x that is negative on the given interval is associated with the negative, with the minus sign, is taken to be negative. And if it so happened that the integration interval from a to b that can fall out any which way from here to here, from here to here, for example, includes the areas where both the function is negative, the function that is being integrated is negative and positive, then for the value, for the numerical value of such a definite Riemann integral is taken what? A net sum of the positive and negative areas that are defined just as I described, and then the overall result right now hangs in the balance between the forces of positive areas and forces of negative areas of the planar regions involved in this problem. That is, if the forces of positive area win out, then the value of such a definite Riemann integral will be positive. If the forces of negative areas win out, then the overall value of the corresponding definite Riemann integral will be negative. It can happen all day long. And sometimes it can so happen that the forces of positive areas and negative areas balance each out perfectly, and then the value of the corresponding definite Riemann integral will be exactly 0. Now that we identified the whole in this problem, what will the smaller and simpler primitive parts be? The smaller and simpler primitive parts in this case will be the thin rectangles that are constructed as follows. The integration interval from the point A to the point B is partitioned into n, where n is a strictly positive whole number, 1, 2, 3, 4, 5, and so on. Line segments, each of which doesn't have to be exactly the same length. The distances between the partitioning points x1, x2, x3, and so on, and xk could be arbitrary. Again, they do not have to be the same. When these distances are the same, this is just a computational convenience, but the way the theory of definite Riemann integrals is put together, the partitioning of the integration interval between a and b into smaller line segment can be arbitrary so long as the largest distance, delta xk, which we compute as the difference between the distance from the origin of the chosen coordinate system to the point xk plus 1 and the distance from the origin to the partitioning point xk can be bound, and that means that when we make that largest difference smaller and smaller and smaller, we can always hit with the corresponding vertical line, the graph of a function f of x. So now that we understand how the partitioning of the integration interval from a to b takes place, we can carry on the next step. Through the points x1, x2, x3, and xk, and so on, we construct the corresponding vertical straight lines. X equals x1, x equals x2, x equals x3, and so on, x equals xk, all the way to x equals xn, which is our right integration boundary point B, that vertical straight line we already constructed in the previous segment. And we also understand that the word partition in mathematics is a very well-defined notion in plain English. Partitioning a certain region means tiling it with smaller parts in such a way that there are no gaps and there are no overlaps between the pieces that delineate that region. In other words, strictly speaking, the union of all the smaller line segments in this case must amount precisely to the integration interval from a to b. Now, the next step in constructing the smaller and simpler primitive part in this case will be the following. Ideally, under the happy path situation, when we deal with pleasant functions, our vertical straight lines, which we constructed through the points that partition the integration interval from a to b, as I explained a few seconds ago, will intersect the graph of the function f of x at the points that are shown over here in blue. For example, the vertical straight line x equals a will intersect the graph of the function f of x over here. The next vertical straight line x equals x1 will intersect the graph of the function f of x here, and so on. And let's say at the point xk, the vertical straight line x equals xk will intersect the graph of the function f of x over here in this point right here. And now comes another arbitrary choice. In other words, we now understand that the partitioning of the integration interval from a to b in general can be carried out in any which way. But in our case, in the problem when we integrate our integrand on the interval what? A equals 0 to b equals pi, it is sufficient to partition our interval into the line segments into n line segments of equal length. And what will the length of these line segments be? Well, in general, the length of these line segments will be what? The difference between b and a, if we agree that b is always greater than a, divided by n, the uniform length, if you will. And in our case, that distance will be what? Since we integrate our function logarithm of the corresponding argument from 0 to pi, the uniform length of each and every smaller line segment that partitions the interval from a to pi will be pi over n, as shown over here. So that partitioning is arbitrary, we understand that, but sometimes for our computational convenience, it is okay to partition the line segment, that is the integration interval, into n line segments of equal length, partition the segment uniformly. This is our arbitrary decision, and then comes the next arbitrary decision. The vertical straight line x equals xk, as I explained, will intersect the graph of the function f of x at a certain point. And it is, to some extent, on the one hand arbitrary, on the other hand, it is natural to take exactly that point as, for example, here, where the arbitrariness of the decision comes to be. That point where the vertical straight line x equals xk intersects the graph of the function f of x can be made arbitrarily by us, by our choice. The upper left corner of the rectangle that is constructed on the base that is represented by the distance between the immediately adjacent partition points xk and xk plus 1, this one, and on the top, that rectangle has its upper left corner on the graph of of the function f of x, and the other vertex of that thin rectangle will fall wherever it will fall on the immediately adjacent vertical straight line, which has which shape? X equals xk plus 1. Now, in general, this placing or construction of the top of the thin rectangle that has the distance between the two immediately adjacent partitioning points as its base can be done in different ways. Instead of putting the upper left corner of the corresponding rectangle on the graph of the function f of x, we can put the upper right corner. For example, if this, let's see, I'll take the blue line segment here, this is our f of x. This is where the, you see, this is where the upper right corner of the primitive rectangle can be placed. This is again arbitrary decision, arbitrary choice, our choice. It is also possible to, for example, place the vertices of our rectangle in such a way. This is, for example, the primitive rectangle in such a way that, for example, it hits the it's cut in the middle by the graph of the corresponding function. You see right here in the middle, on the right or on the left. Here, for demonstration purposes, I decided to put it on the, create the upper left corner of the primitive rectangle on the graph of the function f of x. This is just my choice. You guys should experiment with other choices, but this is precisely what the smaller and simpler primitive part will be. A rectangle that is constructed on the base that is represented by the difference between two immediately adjacent partitioning points xk and xk plus 1 at the bottom, and on the top we choose the upper left corner of the corresponding rectangle to sit precisely on the graph of the function f of x. In a slightly more rigorous treatment, we actually construct two types of primitive rectangles. The one that sit strictly under, as shown over here, under the graph of a function. And then once we tile the entire planar region with this, let's say, in plain English, shorter rectangles, then we will produce what? We will produce an area of the planar region that will be strictly smaller, or will be an underestimate of the area of the corresponding planar region. And then we tile the same region with the rectangles that are precisely stick out above the graph of a function. And when we sum the areas of the smaller and simpler primitive parts, we produce the area of the planar region that is strictly larger than the area trapped under a curve. Then we engage into iterative process of increasing the number of partitioning line segments and then trapping the exact area of the curvilinear planar region between the overestimate and underestimate. But in our case, just dealing with one sum, the so-called left Riemann sum is enough, and that is precisely what I mean when I say that the thin rectangle in this case is a smaller and simpler primitive parts. Now that we carried out the first step of the divide and conquer problem solving approach, that is, we identified the hole, which is the area of the plane trapped above the x-axis under the graph of the corresponding function between the vertical straight lines x equals a and x equals b. And in the next few segments we will see that in our case, depending on the value of the parameter r, remember we have this mysterious real number r, we can have our graph will be strictly above, or it will dip under. But we understand how these things work. If the function is negative, we do the same thing. We partition the line segment in exactly the same way into n line segments, construct the smaller and simpler primitive parts, rectangles on each immediately adjacent pair of partitioning points, and voila, this is our smaller and simpler primitive part. And in general, this is the smaller and simpler primitive part. Now we're done with the step number one of the divide and conquer problem solving approach. And the next step is to figure out what does it mean to solve each and every primitive part. And in the next segment, I will explain what does it mean to solve a thin rectangle that is constructed as I explained. To solve each and every primitive part in this case means to find a way to express the area of the primitive thin rectangle whose construction I explained in the previous segment in terms of the locally available material. And what is the locally available material? The locally available material is first and foremost the usual suspect, the function f of x. Without the function f of x, we're not going anywhere. No function, no integral, no function, no graph, no planar area, and the number n into which we partition our integration domain between points A and B, which basically is figured over here in the denominator, and evidently the boundaries of integration, the point A and point B. And in this particular situation, it becomes evident why we chose rectangles as smaller and simpler primitive parts. Because in general, the area of the curvilinear region is difficult to compute. Let's say we do not know how to do it up front, and an introduction of a new idea is needed in order to do that. But in order to compute the area of a rectangle, we do not really need the introduction of any new ideas. We know that the area of a rectangle is what? Is a product of, let's say, the length of its base and the length of its height. And in our case, both the length of the base and the length of the height can be expressed or captured with the locally available material, which is what? The length of the base of the primitive rectangle is shown over here, b minus a over n, and this is what we refer to as delta xk. This delta xk is shown over here. And what is the length of the height? The length of the height is precisely, remember, we agreed for demonstration purposes to put the upper left corner of the primitive rectangle onto the graph of the function of f of x, but we might just as well put it on the right corner as well. And in other words, the length of the height of our primitive rectangle will be precisely what? The value of the function f of x evaluated where? Evaluated at the point x, k is shown over here. In other words, the product of the value of the function f of x evaluated at the partition point xk times b minus a over n delta xk precisely gives us the area ak of the kth, let's say this will be our kth primitive part. Now that we're done with the second part of the divide and conquer problem solving approach, we found the whole, we divided that whole into smaller and simpler primitive parts. We understand what does it mean to solve each and every primitive part. To solve each and every primitive part, one more time, just to make sure that we're all on the same page, means to write down an expression for the area of the kth primitive rectangle in terms of the locally available material, which is what? Is the product of the function f of x evaluated at the kth partition point k and the width of that rectangle delta xk, which is in general given by b minus a over n, and in our specific case, you guys can write it down because I will be erasing this material frequently, will be pi over n. That is the solution of each and every primitive part. Now we can take a look on how can we combine the solutions of all the primitive parts into a solution of the whole. Very well, we now arrive at the third and the final step of the divide and conquer problem solving approach, where we will figure out how to combine the solutions of the smaller and simpler primitive parts into a solution of the whole. I will be erasing this material over here, guys. Once you understand what is going on, copy it into your records, make sure you have it. But right now I will need this space to explain what does it mean to find a way to combine the solutions of the smaller and simpler primitive parts into a solution of the whole. And as a reminder, we so far know what the whole is. The area between the graph of the function f of x and the real axis x, below and above if the function is positive, and above and below if the function is negative. We know how to partition the integration domain into a number of smaller, shorter line segments, where partitioning is a well-defined mathematical term, which means in plain English tiling the region in question in such a way that there are no gaps and there are no overlaps, and the union of the parts makes up the whole. We understand how the primitive rectangle is formed, and now a way to combine the solutions of the parts into a solution of the whole is mostly transparent, should be mostly transparent by now, because we simply add all the areas, of all the primitive rectangles. We construct a sum, and here we have a little bit of a detail going on, some small nuance. Let's say if we sum the areas AK, here is the nuance. Remember, we put the upper left corner of our primitive rectangle on the graph of the function f of x. That choice corresponds to the so-called left sum, left integral sum, or left Riemann sum, and in this case the coefficients run from 0 to n-1. I will designate it with the letter L for left. And if we do the same thing, but we put the upper right vertex of the primitive rectangle onto the graph of the function f of x, we will obtain the so-called right integral sum or right Riemann sum. In this case, the indexes will run from 1 to n. But in this case, what will happen? Well, ideally, again, under a happy path situations where the function is nice, it is continuous, it doesn't bounce up and down too wildly, everything is good, then in this case will happen what? Well, in one case we will produce an overestimate. For example, you can see these, let me mark them maybe with red. These small rectangles will be sticking out, so to speak. They will be above the graph of the function, and these areas is exactly what will produce an overestimate. So in this case, our summed or total area of all the thin rectangles will be slightly larger than the area under the curve. And if we put the, let's say, the upper right vertex of the smaller and simpler primitive rectangle onto the graph of the function f of x, then here there will be a gap. There will be a small gap over here, and the total sum of the areas of these shorter rectangles will produce an underestimate. And in this case, the area under the graph will only be approximately equal to the sum. And how do we replace the approximate sign with an equal sign and explain and obtain the exact solution? Well, the way we do it is with the help of the limiting process. When we decrease the size of each primitive rectangle, and again, in general, if the partition is arbitrary, we want to get a upper bound on the widest small rectangle from above, upper bound. And in our case, it is evident if we divide our integration interval into n equal parts. We know that if we simply increase the number of these parts, the distance between two immediately adjacent partition points will diminish into 0. So in other words, we take the limit when n tends to positive infinity of this sum over here, either this one or that one. And here is the remark about the arbitrary choices. Whether we construct the left integral sums or right integral sums, doesn't really matter. The way the definite Riemann integral is designed is that it will, if it exists, if these things work out, then the choice of the left or the right integral sum doesn't matter. Not only that, again, if the Riemann integral exists on the given interval for a given function, then this integral will be one and the same regardless of how we partition our integral interval from a to b. What does it mean? It means that, let's say we partition our integration interval into equal line segments as shown over here. We compute the sum, we take the limit, we obtain one number. We partition our integration interval between the points a and b in some other way. We construct, for example, line segments whose length form a geometric progression, for example. Construct the corresponding sum, compute the limit, obtain another number. Partition the integration interval between the points a and b in some other way. Compute the sum, compute the limit, obtain the third number. If all these numbers agree, it is that real number that we assign by definition to the value of the definite Riemann integral of the function f between the points a and b, as explained over here. This is the basic meaning of find a way to combine the solutions of the smaller and simpler primitive parts into a solution of a whole. And if I were to, again, to erase this a little bit over here, you guys understand that in this case, the sum will be somewhat complicated. It will be the sum for the left sum. The index k will run between 0 and n minus 1 exactly of this function f of x k delta xk, and the same thing will happen over here. It will be the value of the function evaluated at the point delta xk, but this time k will run from 1 to n. That's the difference. 1 to n when the sum is right, from 0 to n minus 1 when the sum is left, but the limit is computed the same way, depending, regardless of how we choose to construct our primitive rectangles. And also the partitioning of the integration domain from a to b is also irrelevant any which way. And if under these conditions, when the function is nice, all these variations come out, produce one and the same limit, one and the same real number, that real number is the value of the definite integral of the function f of x on the interval a to b. Now, what does this little bit of theory mean specifically in our case? In our case, this little bit of theory means the following. If we carefully examine the structure of the given integrand, then we will notice that if the absolute value of the real number r is strictly less than 1, then the graph of the integrand on the integration interval will look as follows. Which means that on the integration interval from 0 to pi, the graph of our integrand will precisely intersect the x-axis, and this will be exactly the case which I mentioned earlier, where we will have both negative areas where the graph of the function dips under the x-axis, and the positive areas where the graph of the function f of x on a given interval stays above the x-axis. In contrast, when the absolute value of the real number r is, here I'll write it down, strictly larger than 1, that means that r again can be both negative and positive, then the graph of the integrand at hand will look as follows. Which means precisely that if the value of r is positive or negative but is larger than 1 or less than 1, then the graph of the function on the integration interval of interest from 0 to pi will be strictly above the x-axis, and we will be dealing with the classical case. And for completeness, here is the shape of the integrand at hand, where the value r is precisely 1. Please take a look. And for completeness, here is the graph of the integrand on the integration domain when the value of the real number r is negative 1, negative 1. Please take a look. And what that means to us is that we essentially identify 3 interesting cases for the values of the real number r. When the absolute value of the real number r is strictly less than 1, when the absolute value of the real number r is strictly larger than 1, and the third case is when the absolute value of the real number r is exactly 1. So that means to us that in the most general setting, the real number r can be both positive and negative. The case when r equals 0 we already excluded early on for the reasons that I explained earlier. However, in the grown-up mathematics, when you will be taking, for example, a course on maybe higher level real analysis or complex analysis or topology, you will get introduced to the notion of a metric space. So what is a metric space? A metric space is a pair shown over here with round parentheses where x is a certain set and d is called a distance or a metric, which is technically a function from the Cartesian product of x times x to the set of real numbers r. But it is important that this distance or this metric obeys these 4 very important rules. First of all, the distance between any 2 elements of that set x is strictly not negative, greater than or equal to 0. You see, this is the one of the key points in the properties of a metric. Next, the metric will be equal to 0 if and only if the distance that is measured between 2 objects measures the difference between the same objects, x and y is one and the same object. Then the distance collapses into 0. Then the distance has the property of the symmetry. The distance from the element x to the element y is the same as the distance from the element y to the element x. And the last one, you will all recognize the so-called triangle inequality captured over here. That is the distance between the distances across 3 distinct in general objects. So under this angle, if we already saw that the real number r can be both positive and negative, but if we step into our topological interpretation and keep the distance r interpreted as strictly positive magnitude, then there is a pleasant geometric interpretation for the argument of our integrand, for the argument of the logarithmic function. What is it? Well, first, the geometric interpretation of r as the distance from the origin of the chosen coordinate system x, o, y between and the point o and the point r shown over here. In other words, we fix a traditional orthogonal coordinate system x, o, y, pick the origin, throw a point r into the upper half plane, and we measure the distance from the origin of the chosen coordinate system and that point r. That distance is the geometric interpretation of the parameter r, parameter r, parameter r. Under that interpretation, the entire argument of the logarithm, this scary looking expression over here, according to the middle school law of cosines, is what? Is the square of the distance between the point 1, O, this point right here, and the point R. And because the value of the argument of the angle of the trigonometric function of cosine varies between what? 0 and pi. Consequently, that means that our point R roams the upper half plane. But because of the interesting values that we described over here, that we discovered when we analyzed the behavior of the integrand, we see that when the point R is located strictly inside the origin-centered unit disk in the upper half plane, and what I showed over here in blue is exactly that, origin-centered half unit disk, because the radius of this disk is precisely 1. So the case when the real number R is strictly positive but less than 1, then that means that the point R is located strictly inside the origin-centered unit half disk, and the geometric interpretation of the argument to the function logarithm, which is our integrand, is what? The square of the distance from the point, this will be rho squared, the square of the distance between the point 1, 0, the point 1 that sits on the real axis over here, and the point R that's inside the origin-centered half unit disk located in the upper half plane. Where does it come from? It comes obviously from the middle school law of cosines, which says what the square of this in the triangle OR10, what is the length of this side? Well, the square of that length of that side, according to the law of cosines, is what? The square of the first distance, which is 1. This distance over here is 1. 1 squared is 1, plus the square of the length of the second side of this triangle, OR is R squared, minus twice the product between R, 1, times the cosine of angle between them. This is the angle theta shown over here, and voila, we have our argument to the logarithm. Now, when the absolute value of the real number R is equal precisely to 1, that means in general it can be plus 1 or minus 1. In our case, under the topological interpretation and in the metric space sense, that means that that case corresponds when the point R, the green chalk, let me grab the green chalk, then the point R is located somewhere here precisely on the periphery of this, somewhere here or here or somewhere over here on the periphery, precisely on the periphery of the origin-centered half unit disk. And the case when the real number R again is strictly positive but greater than 1, that means that in this case the geometric interpretation of the argument of the logarithm, which is our integrand, is what the square of the distance between the point 1, 0 and the point R that roams the upper half plane somewhere outside, is located somewhere here or somewhere over here, that is strictly in the upper half plane and outside the origin-centered unit half disk. Now, with the preliminaries out of the way, let us construct our right Riemann sum for the given integrand and see where it takes us. If you were paying attention so far, then how would you write down an integral sum representation of the given definite Riemann integral? Well, we know that such a representation begins with the limit when n tends to positive infinity of what? Of the finite sum, let's write it down here, that runs between k equals 1 and n, because in this case we choose the right integral sum of what? Of the function that we're trying to integrate, the logarithm in base e of 1 minus 2 times r times cosine of a certain argument, we'll figure it out what it is in a second, plus r squared, like so, times what? Remember that this expression over here shows what? Shows the height. It shows the height of the primitive rectangle at the point, which one? At the point xk. Remember, we partitioned our integration interval into n equally sized line segments of length, which one? Pi over n. And then what is the displacement of the point xk with respect to the origin of the chosen coordinate system? Correct. That displacement must be k smaller line segments, each of which is pi over n units of length long. And that means that we evaluate our function. Whenever we see x, we replace x with what? K times pi over n. This is again the displacement of the partitioning point xk from the origin of the chosen coordinate system, and it so happens that our integration interval runs from 0 to pi. So this is the expression, and don't forget that we have to multiply this by what? By the width of the base, or the length of the base of our primitive rectangle, and that width is how much? Is pi over n. But does pi over n depend on the value of the summation variable k in our sum? No, it does not. Consequently, we can factor out this formation pi over n and put it in front of the sign, and voila, we have our right integral sum representation of the given definite Riemann integral. Remember that we put the upper right vertex of the respective primitive rectangle on the graph of the function f of x, and that is why our summation index runs from 1 to n. And now I want to make sure that everyone in the audience understands that in order to evaluate this expression over here, we cannot flip it back to the original definite Riemann integral, as it is frequently done on various problem-solving forums, where the seemingly convoluted limit of some sum pops out, and the question is, what is the value of this limit? Here, in order to evaluate the given definite Riemann integral using the divide and conquer problem-solving approach, or by the book, as a limit of a certain integral sum, and in this case we took the right integral sum, we need to take on the respective sums and the respective limits head on, using a machinery that is different from the machinery that was developed for evaluating the definite Riemann integrals, not via limits and sums. As such, how can we do that? Well, one of the first things that comes to mind is the fact that we have the logarithmic function as our summand. And what identity comes to mind when we look at the sum of logarithms? Exactly. We recall that for any two positive real numbers, it is the case that the logarithm of a times b is the logarithm of a plus the logarithm of b. A and b are strictly positive real numbers because the logarithmic function is defined only for those. And if you have learned this identity, for example, sometime in later in the middle school or maybe in high school, and you thought that this is it, this is actually not it. This is a very important relationship that reflects a certain group isomorphism. In other words, this here relationship tells us that structurally the set of positive real numbers under multiplication behaves in exactly the same way as the set of all real numbers under addition. In the first case, we get the so-called infinite commutative multiplicative group of positive real numbers, with 1 being the identity of the group. And in the second case, we get the infinite commutative additive group of real numbers with 0 as the group's identity. Anyway, once we have this identity front and center, what can we say about the sum of logarithm? Because what we have over here is basically logarithm of A plus logarithm of B plus logarithm of C, and so on n times. What this identity tells us is that we can roll up the sum into a product, and then instead of computing the sum of logarithms as shown over here, what can we do? We can rewrite this expression as follows. It will still be a limit when n tends to positive infinity of pi over n times what? The logarithmic function evaluated at Pn, where Pn will be our what? The finite product of the arguments. So this will be a product that runs with respect to the variable k, where k varies from 1 to n still. And what are the factors in this product? 1 minus 2r cosine of k pi over n plus r squared. Write this down because I will be erasing this material frequently, and you guys keep up with what I do on my board in your paperwork. And overall, what do we see? We see at least two things. If we want to evaluate definite Riemann integrals by the book as limits of the certain integral sums, we need to be able to, without getting too clever about it, we need to be able to evaluate finite sums. And in some sense, in that direction, we may want to develop, let's say, the theory of computing the finite sums. And number two, we need to be able to evaluate the corresponding limits and develop the theory of limits, which by now is actually very well developed. And now we see that instead of the sum, we have to evaluate the product. And how can we do that? Well, we will consider the computation or evaluation of this finite product in the upcoming segments. Wonderful. So now we will evaluate this here finite product as follows. I will do it my way. If you guys have a different idea, don't be shy. Share your beautiful, elegant, and crisp idea with the rest of our community in the comment section. I will attack this finite product piece by piece. That is, when we look at this product, especially given the presence of the trigonometric function of cosine with the argument k, with the argument of the function having that specific structure, what is the first thing that comes to mind? The first thing that comes to mind is that when k reaches the value of n, k becomes n, and in the numerator and n in the denominator cancel out. And what happens over here? We get the cosine of pi. That is, let's say, if k is equal to n, then what happens to the trigonometric function of cosine? We have cosine of k times pi over n, which is cosine of n times pi over n. We see here that n in the numerator and n in the denominator cancel each other out. We obtain the value of the trigonometric function of cosine evaluated at the argument pi. This is what? This is a synonym for -1. And how can we rewrite our finite product then? Well, our product, finite product Pn, becomes what? When the cosine becomes -1 in this product, what happens to the factor, to the corresponding factor? Well, in this case, we have 1 plus 2 times r plus r squared. Would you agree? 1, negative 1 times negative 1 becomes plus 2r plus r squared. And what is that? That is a perfect square. Exactly. This becomes 1 plus r squared. Wonderful. And that means that we can rewrite our finite product as follows. This factor over here does not depend on the multiplication dummy variable k, so it can be factored out. So we write 1 plus r squared times the product constructed with respect to the variable k, which runs as follows. From 1 to n minus 1, it is important to realize here that the upper bound of this product is now n minus 1, not n, but n minus 1. One more time, n minus 1, not n. And then the rest of the usual suspects. Write this down because I will be erasing this material again. And what do we do next? Again, I will proceed one way. If you guys have a different idea, share this idea with our community in the comment section. As a heads up, in order to evaluate this finite product, I will enlist the help of complex numbers. If you're seeing what I'm about to show you for the first time in your life, then this will come across as next to impossible magic. But if you get to know complex numbers, this will be a kindergarten variety manipulation. As such, recall that the polynomial, let's designate it as too many p's in our case, let's say q 2n of z. So here z is a complex number that has the following shape. Z raised to the power 2n minus 1 can be represented as a finite product precisely, where k varies from 0 to 2n minus 1 of the terms that are linear in the variable z. This is basically the fundamental theorem of algebra. We can decompose such a polynomial into a product of the terms, each of which is linear in z. What are these numbers omega to n k? The numbers omega to n k are complex numbers which are the roots of the following equation. Z raised to the power 2n minus 1, that is equal to 0. And how can we rewrite this equation? Well, let's do it together. Let's add 1 to both sides of this equation. And what will we get? We'll get z to the power 2n, that is equal to 1. Over here, officially, let's write it down, maybe over here. Z is a complex number, and n is a non-negative whole number, 0, 1, 2, 3, and so on. How do we solve this equation over the field of complex numbers? Well, here's one way. We can represent each number, each complex number, on either side of the equal sign in their exponential form, and I'll do it suggestively, writing it down as follows. If the complex number z is represented as, let's say, represented as r times e to the power I theta, then if we raise both sides of this equality to the power 2n, what will happen? We will have the radius vector associated with the point to which this number z corresponds raised to which power? To the power 2n times, here I'll write down e raised to each power 2n I theta, and that will be equal to, how do we represent the complex number 1 in this case? Well, it will be 1 times e raised to the power I times 0, and because the complex valued function has the period of 2 pi I, this can be written also plus 2 pi I times k, where k in general varies over the entire set of integers or whole numbers that are negative, positive, and 0. Now what do we do? Well, now we compare the moduli of each complex number that we have in hand, and because they need to be equal, if there's an equal sign between these two complex numbers, their moduli must be equal. In other words, r to the power 2n must be equal to 1. I will suggestively use the same color. Here we need to understand that we will execute maybe somewhat funny maneuver for many people. Here 1 is taken to be a complex number, that is why it has this representation. But in the exponential representation of real numbers, we have for their moduli is a strictly real number. So in this case, to cut the vicious circle, when we extract the 2nth root of 1, what do we get? Over the field of real numbers, the only way this equation can hold if what? If r is equal to 1, precisely. This is the only way it works. And geometrically, what does it mean? Geometrically, it means that in the complex plane, the points which correspond to the solutions of this equation are located where? They're located on the periphery of the origin-centered unit circle. Now that we equated the moduli of these two complex numbers, what do we do next? Exactly, next we equate the powers of the exponents on either side of the equal sign. And what does that mean? Well, in this case, I'll use the yellow chalk again. We will have to say that 2 times n times I times theta must be equal. 0 can be discarded, so we'll have 2 times pi times I times k, where k varies over the entire set of integers. In this equation, what can we do? 2 and 2 cancel each other out. The imaginary unit I and I cancel each other out. And what do we have for the value of theta? Well, for the value of theta, where we will index it with n, depending on k, that's how we will write it. What expression do we have? We have precisely k times pi over n. This is our argument of the complex number, of all the complex numbers that are the solutions of this equation. And what do we see already? Well, we see already this is the usual suspect, k pi over n. This is precisely the argument to our trigonometric function of cosine. And what does that mean? Well, when we reassemble or reconstruct our complex number in this form, what will these numbers look like? Well, these numbers we will designate with omega over here. And what is the structure of these numbers? Let's write these numbers over here. Omega to n of k. Well, the modulus of all these numbers r is 1, so we can omit 1. And what is the argument of these numbers? Well, this argument is shown over here, so we will write it as an exponential function of what argument? I times k pi over n. This is the exponential form of the roots of our equation over here. And in the trigonometric form, I'll separate it here. What will we have? We'll have cosine of k pi over n plus I times the trigonometric function of sine evaluated at the argument k pi over n. This is nothing complicated. This is just the basic arithmetic of complex numbers, and that is how we develop it. Now we need to carefully think about this usual suspect over here. In general, yes, this number k varies over the entire set of integers. However, what will happen when k varies over the entire set of integers? Well, we know that the exponential function has a period, what? 2 pi I. And that means that the distinct roots, these are called roots of unity, so the distinct roots of unity will be generated only when k varies. Let's put the comma over here. When k varies over the so-called set of least non-negative residues modulo 2n, so 2n minus 1. This is the set of distinct roots of unity, where k varies from 0 to n minus 1. And that is fairly easy to see. Let me just maybe write it down over here for you guys. Let's say when k reaches the value of 2n, what will happen? We put k into the numerator here, 2n, n in the numerator, n in the denominator cancel each other out. So what do I have? The exponent of I times 2 pi. This is precisely the case of 2 pi. So we come back to the root of unity that corresponds to what? K equals 0. And let's say we grab the next one. Let's say k steps over to n and becomes 2n plus 1. What will we have in the expression for the argument of our roots of unity? Well, in this case, let's do this carefully. We'll have I and then 2n plus 1 over n times pi. And look at what happens. N and n cancel each other out if we break up this. 2 plus 1 over n pi. And again, there pops out the period of the complex valued exponential function 2 pi I. So now we understand that the distinct roots of our equation, or the so-called zeros of our polynomial over here, the simple zeros of our polynomial, are given by this formula over here. This is the whole thing that we keep track of. This is the exponential form of the 2nth roots of unity. In this case, this is their trigonometric representation. This is how the value k varies for these roots of unity to be distinct, and we will need both of these expressions in the upcoming manipulations. So I suggest that you guys write it down, and I'll take a short break and erase the material and prepare it for the next step when we will evaluate our finite product Pn. Even though all the manipulations that we are about to carry out can be done algebraically or purely abstractly, if the students are told a geometric interpretation of the complex roots of unity, then somehow their understanding of the whole situation becomes better, and that understanding lasts longer. As such, it should be understood well first that as a mathematical object, a number is not a geometric point, and conversely, a geometric point is not a number. However, in a straightforward manner, it can be shown that between the set of complex numbers and the set of points in the complex plane, there exists a bijection, or a one-to-one correspondence, which means that to each and every complex number, there corresponds a unique point in the complex plane, and conversely, to each and every point in the complex plane, there corresponds a unique complex number. Then, as we already mentioned in the previous segment, to each and every 2nth, in this case, root of unity that corresponds a point in the complex plane that has the modulus of 1 or the radius vector of 1, which means that each and every such point that corresponds to a root of unity sits precisely on the periphery of the origin-centered unit circle as shown on the right-hand side screen over here. And it is also should be evident that these points on the periphery of the origin-centered unit circle are not placed uniformly, but they are not placed in some haphazard way, but they are sprinkled over the periphery of the circle uniformly. Why is that? Well, recall from the previous segment that in the exponential form, the argument of each such root of unity is what? Ik pi over n, or an exact integral multiple of one and the same number, pi over n. And that precisely means that the angular displacement or the angular difference between any immediately adjacent points on the periphery of the origin-centered unit circle, each of which corresponds to the root of unity, is what? Is one and the same number, pi over n. So the distance between these 2 points, the angular distance between these 2 points is pi over n. The distance between these 2 points, the angular distance is pi over n. The angular distance between these 2 points, pi over n, and so on. And what does that tell us? Well, that tells us that all the points that are sprinkled uniformly over the periphery of the unit circle that is origin-centered, that correspond to our roots of unity, form what? They form a regular polygon on 2n vertices in this case. And again, that polygon is positioned in the complex plane, not in some haphazard way, but in a very specific way. That is, the vertex of the polygon that corresponds to the root of unity that has the index of 0, or in some sense our first root, is positioned on the positive branch of the real axis at the point 1, 0 shown over here. In plain English, that root has the fancy name omega 2n 0, but this is basically 1. And if we have 2n such roots and 2n roots geometrically transcribe what? A complete circle of 2 pi radians, then half of these roots, then which associated with what? With the number n, correspond to which angular displacement? 2n associated with 2 pi. 1/2 of 2n is n. 1/2 of 2 pi is what? Pi. Precisely the argument of the complex root of unity in our case that is indexed by number n will be precisely pi, which means that geometrically that root corresponds to a point or a vertex of our regular polygon that sits precisely on the negative branch of the real axis at the point -1, 0 as shown over here. As such, in this geometrically and algebraically beautiful arrangement, we have 2n vertices and the regular polygon constructed on them. And these vertices are positioned in such a way that 2 of these vertices, precisely 2, are positioned on the real axis. And then the remaining, how many? 2n minus 2 roots, or 2n minus 2 vertices or points in the complex plane, are sorted into 2 equally sized piles. One such pile, shown in red over here, lives in the upper half plane, and the other such pile, shown in green over here, lives in the lower half plane. And now that we have the visual understanding of how exactly our roots of unity correspond to the geometric points in the complex plane, the rest of the computation should be very, very straightforward. You guys probably can carry it out by now by yourself. You do not need me, but let us do it together. So now let us chip away at our product representation of our polynomial based on the fundamental theorem of algebra as follows. Let us accommodate the very first index k equals 0. In plain English, our fancy omega to n with the index 0 is what? Is 1, exactly. So this product can be rewritten as follows. Z minus 1, we factor this guy out, times the product that now runs from 1 to 2n minus 1, and then z minus omega 2n sub k, like so. That much we understand. No magic over here. We simply took the value of k that is equal to 0. That value corresponds to our logically first root of unity. This is a number 1. We factored this representation of the factor of our polynomial out, and then we get the product that runs from 1 to n minus 1. So far, so good. Excellent. Now we do the same thing with the root of unity that sits on the negative branch of the real axis, and that is basically number minus 1. And how do we rewrite our product then? Well, in this case, we will factor out not z minus 1, but z minus minus 1, z plus 1. And then here we need to be careful, because now we're taking out in our notation the value k that is equal to n. What do we do? Here k varies from 1 to n minus 1. This is basically accommodation of these roots that live in the upper half plane, because we took out, remember, the very first root. So this will be z minus omega to n k shown over here times what? We have to skip basically the k equals n in our notation. It gets awkward, so we write it as a product of two products. Here k varies from where? We skip n, k equals n, so we pick up where? From n plus 1. We pick up over here our product. Then we step over the periphery of the unit circle all the way over here to this gentleman, to this guy right here, 2n minus 1. And we essentially have the same expression, minus omega 2nk, like so. That much should be understood by everyone. This is not complicated. So here, essentially, we have one and the same product, but it should be understood that the index over here does not vary uniformly from here to here, but it skips a beat, so to speak. It skips the value of k equal to n. That corresponds to this root and this vertex of our regular polynomial of degree 2n. So let's rewrite this in a little bit more compact form. What can we do? Well, we can roll up this product over here, a minus b times a plus b. This is middle school arithmetic. What do we have? We have z squared minus 1 times the product that varies over the variable k from 1 to n minus 1. And the factor here is linear in z. This is the rest of our roots of unity times the product with respect to k, which varies from n plus 1 to 2n minus 1. And exactly the same factor, nothing complicated over here, 2nk. But now you guys can proceed without me on your own. You do not need me. I will take a short break and erase this material over here to carry out the next computation. But what is the technical idea for carrying out the next computation? Well, if we want to compute this product, it would be nice to roll it up into one where the variable k choose on the material of the product in a way that is uniform. K varies uniformly from 1 to, let's say, n minus 1, or whatever the case may be. Having two products that vary over the same essentially variable, but this variable ranges in different ways, is awkward. So how can we roll it up into one product? This is the thing that we will do in the next segment momentarily. This is again a purely algebraic fact, which says that if a polynomial has complex roots, then these roots necessarily come as conjugate pairs. And what does a conjugate pair of numbers correspond to geometrically? Well, geometrically, a conjugate pair of complex numbers corresponds to 2 points in the complex plane that are situated symmetrically with respect to the real axis. And because of the way in which our regular polygon on 2n vertices was constructed, it is not that difficult to show that all our roots that I suggestively partitioned into green, let's say, roots that live in the lower half plane and the red roots that live in the upper half plane. How many of those? 2n minus 2 over here, 2n minus 2 over here are what? Exactly, they are the conjugate images of each other, because every such pair is displaced vertically from the real axis by exactly the same amount. For example, how can we prove that? Well, that doesn't have to be high school proof. It can be middle school proof that is based on trigonometry. For example, for these 2 points, let's say take these 2 points. One angle, the same angle. So the projection of this line segment onto the straight line that is parallel to the imaginary axis is what? Is one and the same. This will be the sine of this angle, this distance and this distance. Let's say these 2 points. Again, the angular displacement of this point and of this point with respect to the real axis is one and the same. In this case, it will be 2 pi over n, 2 pi over n. And what does that mean? It means, again, that the vertical component of the radius vector of here of length 1, this one, and this one will be what? Sine of 2 pi n, the axis will be the same. So the displacement of each pair, like this, of complex roots of unity in our case, is what? Is exactly the same with respect to the real axis. And we will take advantage of this fact. In other words, let's do it over here. So guys, in the next segment, we will jump into the computation. What can we say in this case? Well, in this case, we can say what? We can say that omega 2n, here we change the argument. Look at this, 2n minus k. And these complex roots correspond to the vertices of our regular polygon that live where? These are the green vertices that live in the lower half plane. This vertex corresponds to the root with the index 2n minus 1. This vertex corresponds to the root 2n minus 2, and so on. What are these numbers? These are the conjugate pairs, omega 2n of k with the straight line above it. Now, conjugation is an important operation, but it's not a field operation. And over the set of complex numbers, we have 2 such non-field operation. The first non-field operation is the conjugation, and the second non-field operation is what? Taking the modulus of the complex number. So using this observation over here that has a straightforward geometric interpretation shown over here, in the next segment we will basically roll this product into one, and then we will see where it will take us. Wonderful, based on the observation that the roots of unity in our case can be partitioned in a way that is shown over here, and 2n minus 2 red roots that live in the upper half plane are the conjugate images of the 2n minus 2 green roots that live in the lower half plane, captured algebraically over here. That means that our product that represents one way in which the polynomial z to the power 2n minus 1 can be written is what? Is the product of the following linear terms: z minus the root of unity with the index k times z minus conjugate image of the same root in the left product shown over here. And what unfolds next is, again, nothing more than the good old middle school arithmetic. All we have to do now is open up the parentheses or represent this product of two linear terms in a more advantageous way. And how do we do it? Well, again, no intellectual voltage here. Z times Z is what? Is Z squared. Would you agree? We simply carried out all the material from the top line over here onto the next line. Z squared minus 1 times the product with respect to the dummy product variable k that varies from 1 to n minus 1. But now, again, it is important that we rolled up the two products that we saw in the previous segment on the bottom of the screen into one where the index varies uniformly. And the reason we could do that precisely because of this beautiful geometric symmetry of the roots of unity. So now next we have to multiply z by z and obtain z squared and write it down. What is the next thing? Z times negative conjugate image of the root, and then negative root itself times z. What does it tell us? It tells us that we can factor out negative z, and what will we have? Minus z times the conjugate minus z times the root itself. So here we'll have the sum of the root and its conjugate image. Sum. And what else? What will be the final term? Well, here we will have negative root of unity times negative conjugate image. So that means that we'll have the plus sign. We'll have the plus sign. Let's carry it over here. What will we have here? Well, instead of the sum, we'll have the product of the root of unity and its conjugate image. Look how beautiful these things fall into place. Close the parentheses, put the horizontal bar on top to designate that this is the conjugate image of this number, and this is it. Essentially, this is it. So we now have the multiplicative representation of the polynomial in the complex variable z that has the shape z raised to the power 2n, and the whole thing is reduced by 1, as shown over here. Z squared minus 1 times the product that is carried over with respect to the dummy product variable k, which varies from 1 to n minus 1, and the structure of the factor over here is the following. Z squared minus z times the sum of the root of kth root of unity and its conjugate image plus the product of that very same root and its conjugate image, and that is all there is to it. And now again we whittle down that product little by little. In the next segment I'll take a short break, and in the next segment we'll see what the sum over here may be scary looking, but it's not really that scary. What does this sum of a kth complex root of unity and its conjugate image amount to? Excellent. Let us now evaluate the sum of the kth root of unity and its conjugate image. I designated that sum over here, and maybe let us do it with the blue chalk just to bring in some visual contrast over here. We'll do it over here. We will evaluate the sum of the kth root of unity and its conjugate image using what? Using the trigonometric form of the corresponding roots. And after that, in the next segment, we will evaluate the product of the root and its conjugate image using what? Precisely using its exponential form. So in the trigonometric form that was written on the right-hand side of your screen a few segments ago, go back to your records, pull them out. Those of us who pay attention remember this by heart. We don't really have to go to the paperwork. We can actually do it without pen and paper, all seeing all these things in our mind's eye. But for the sake of everyone in the community understanding what we're doing, we write down the trigonometric representation of the kth root of unity here will be what? 2k pi over n plus I times the value of the trigonometric function of sine evaluated at the argument k pi over n. But remember that much. And what is the sum? Here the sum plus, again, the value of the trigonometric function of cosine evaluated at the same argument k pi over n. But because this is a conjugate image, what does it mean? It means that there is a negative sign in front of the trigonometric function of sine, which is evaluated in exactly the same argument. And what do we see? We see a miracle of cancellation. The purely imaginary terms over here cancel each other out. And what do we have in the end? In the end, we have cosine evaluated at the argument k pi over n, and another cosine evaluated at the argument k pi over n. And how many copies of these trigonometric functions of cosine are there? Exactly, there are two copies. 2 times cosine k pi over n. And what is that? This is precisely, if you go back to your records, you will recall that this is precisely one of the summands, which is the argument to the finite product and to the argument to our integrand, the logarithmic function. Very good. In the next segment, I will erase this. Make sure you guys keep track of this computation over here. I will erase this, and in the next segment, we will carry out the computation of the product of the kth root of unity and its conjugate image. Very well, now that we evaluated the sum of the kth root of unity and its conjugate image, in this segment we will evaluate the product of the kth root of unity and its conjugate image written over here. I'll do it, let's say, in red so it's easier for you guys to see. This product is over here, the root, its conjugate image, and in order to do that, instead of the trigonometric form, we will do what? We will use the exponential form. So here we'll carry out this computation as follows. We'll write down the exponential representation of the kth root of unity, which is k times pi over n times the exponential function of the conjugate image, which is what? Negative. This will be I keep forgetting this I all the time, I k pi over n. And what do we do now? Again, we use one of the fundamental properties of the complex valued, in this case exponential function, and we rewrite it as 1. We move everything under the 1 exponent, and this will be what? I times k pi over n minus I times k pi over n. And what is it? I k pi over n minus I times k pi over n is what? This is the exponential function evaluated at the argument 0. And what is that? This is precisely 1. In other words, this product over here, as we just proved, is equal to precisely 1. And what does that mean? That means that multiplicatively, our favorite polynomial in the complex variable z shown over here can be represented as follows. As the first factor of the multiplicative representation of the polynomial z raised to the power to n with the whole sum and reduced by 1, we will have the following expression: z squared minus 1 followed by n minus 1 factors, each of which has the following shape: z squared minus 2 times z times the value of the trigonometric function of cosine evaluated at the argument k pi over n plus 1. And we all understand where did this expression come from. In the positive unity over here, we recognize what? In the positive unity up there, we recognize the product of the 2nth root of unity number k and its conjugate image. And in the product 2 times cosine k pi over n, we recognize the sum of these two roots. And now, if we go back to our carefully kept record and look at the expression for the finite product Pn, which is the argument to the logarithmic function, which is the integrand in our case, what we will see? we will see that what we need is almost the same thing as what we have, what we deduced, with the difference that in the finite product shown on the left-hand side of your screen, we have the complex variable z, and in the same finite product shown on the right-hand side of your screen, we have the real variable, if you will, or the real number r. Consequently, in order to express what we need in terms of what we have, we take what we have and in it uniformly replace the complex number z with the real number r. And in this case, we will have what? Our finite product, r squared minus 2r cosine k pi over n plus 1, represented as actually a function that is rational, both in c and in r. In r, it will be r raised to the power to n minus 1 in the numerator, and r squared minus 1 in the denominator. Let's just write down that expression for this finite product Pn. It will be 1 plus r squared times what? R raised to the power to n minus 1 divided by r squared minus 1. And we can massage this a little bit in the middle school arithmetic style by moving the denominator of the rational function under the expression shown over here, 1 plus r squared y, because in the difference of squares we have what? R minus 1 times r plus 1. So we write this as follows: 1 plus r squared divided by r plus 1 times r minus 1 times r to the power to n minus 1. And what do we see? We see that one copy of r plus 1 in the denominator and one copy of r plus 1 in the numerator cancel each other out. And what do we have? We have the following expression. Let's write it down this way: r plus 1 over r minus 1 times r to the power to n minus 1. This is our result. And if we go back, then our Poisson definite Riemann integral can be rewritten as follows: r as a limit. We already went through all the motions. When n tends to positive infinity, pi over n times the natural logarithm of what? R plus 1 over r minus 1 times r to the power to n minus 1. And if we remember, this is the representation of the definite Riemann integral associated with the name of the French mathematician Simeon Poisson, cosine of x plus r squared dx. This is our result so far, and now we understand well why we had to exclude the special case when the absolute value of r is equal to 1. In that case, we may have a division by 0, which is not allowed, so we will evaluate this integral separately in a few minutes, and it's not that complicated. But here, with the case when the absolute value of r equal to 1 is excluded, we now understand, it becomes evident that we're about to take this limit, so we need to be careful about the value of r, because this value is raised to the power to n, and our limit depends precisely on that predicate, if you will. N tends to positive infinity. So here we distinguish two cases. When the absolute value of r is less than 1 and the absolute value of r is greater than 1, because we already see what's happening. When the absolute value of r is less than 1 and that magnitude is raised to the increasingly larger and larger powers, what will we have? The limit of that expression will evidently be 0, but we'll discuss this in more detail in a few seconds. I'll erase this material and prepare the discussion, or for the analysis of the case, we'll compute this limit over here first, when the absolute value of the real number r is less than 1. When the absolute value of the real number r is strictly less than 1, then we need to evaluate the following limit, which is directly associated with the Poisson integral over here. I wrote down the condition that the absolute value of r must be strictly less than 1 as the subscript notation over here. And how do we attack this limit? Well, here first we will use the theorem from real analysis or whatever else this course will be called in your country, which states that the limit of a product is equal to the product of the limits, provided that the limits exist. And in this case, the limits do exist. In other words, the limit of this product, pi over n times the value of the natural logarithm, will be equal to the product of the limits separately of this guy, limit pi over n, where n tends to positive infinity, times the limit of the logarithm of the given argument. But we remember from the previously proved facts, the logarithmic function of the real argument over here is what? It is continuous everywhere it is defined, and it's actually monotonically increasing when the argument increases. As such, we have the right to carry the limit sign through the function name into the argument. And here in the argument, what will we have? We will have the most interesting limit over here, which will be what? Let's think about this one. Limit when n tends to positive infinity of r raised to the power 2n when the absolute value of r is strictly less than 1. What is that limit? Well, from the previously again proved material exercises or however else you guys studied this limit will be evidently what? This limit will be big fat 0. That much we know from the theory of limits. In other words, what does that mean? It means that this term over here vanishes. We have negative 1. We carry this negative 1 into the denominator. And what do we have? We have times the value of the logarithm evaluated at which, how would we write it? We can write it 1 plus r divided by 1 minus r. This is our limit. Now, it should be understood that this value of the natural logarithm shown over here on the far right hand side of your screen is what? Is a constant real number. And again, we go back to real analysis to the corresponding theorem. The limit of a varying quantity times the constant is the constant times the limit of the varying quantity. And again, is everything up to snuff over here in this case? Well, if r is small and positive, then to the positive number in the numerator one, we will be adding a small positive number less than 1. And this number, the result will be positive, strictly positive real number. Here from 1, we will be subtracting a number that is strictly smaller than 1, another positive number in the denominator. Positive numerator divided by the positive denominator is a positive real number. This is a finite number. And once we carry this constant real number from under the limit, what is this limit over here? This limit over here? Evidently, this limit is 0, and what we have here is a big fat 0, and the value of the integral of the Poisson integral in this case, when the absolute value of r is strictly less than 1, is 0. And next, we will consider the case when the absolute value of the real number r is strictly greater than 1. In the case when the absolute value of the real number r is strictly larger than 1, which I highlighted here in red for better contrast so that we do not confuse this case with the previous case, we have to evaluate essentially the same limit, but this time the number r, which could be both negative and positive, is raised to the power 2n, is greater than 1. And in this case, again, look, we are raising this number r to what? To the power that is even. So in some sense, whether this number positive or negative does not really matter. So how do we evaluate this limit in this case? Again, do not just, guys, watch my solution bluntly and without any personal effort, as we explained in season 1 episode 2. This is a good time point for you to put the video on pause, walk away from the computer, think on your own, try to solve this problem on your own all the way to the end, and then come back to our video and compare your ideas to ours. So my idea here is the following. We multiply the argument of the logarithmic function by r raised to the power n, and we divide it by the same number. In this case, this transformation is neutral. R raised to the power 2n divided by r raised to the power 2n. 1 is the multiplicative identity for positive real numbers or for all real numbers. And this does not affect the value of the argument, does not affect the value of the logarithmic function, does not affect the value of the entire limit. So from the value of the limit perspective, this transformation is neutral, but it buys us a competitive advantage. Remember that according to one of the fundamental properties of the logarithmic function, for any two real numbers, strictly positive real numbers AB, the logarithm of the product AB is equal to the sum of logarithm A and logarithm B. So here we carve up the argument of our logarithm as follows. We take this to be our proverbial A, highlighted in red and in green. This will be our proverbial B. How do we write this logarithm then? Well, in the first case, it will be the limit when n tends to positive infinity, pi over n times the logarithm of what? We will have r plus 1 over r minus 1 times r raised to the power 2n minus 1 divided by r raised to the power 2n plus the limit. Let's write it down carefully. When n tends to positive infinity of what? Pi over n times the value of the, I'll leave some room over here because you'll guys see where this is going, r raised to the power 2n. Would you agree? Logarithm of a plus logarithm of b, but b is raised to the power 2n. So by another fundamental property of the logarithmic function, what can we do? We can move this suspect over here. So this will become 2 times n times the logarithm of, in this case, r. And evidently here we need to say absolute value of r. The logarithm in real numbers is defined only for the strictly positive real numbers. What do we see over here? N in the denominator and 2n in the numerator cancel each other out. The expression then becomes void of any varying material. Limit of a constant is a constant, so we are good over here. Let's talk about this limit over here again. The number r, which could be negative and positive, is raised to an even power that grows without bound. That number becomes very large, and that means that compared to 1, we can, let's say, neglect 1 in this case when n grows without bound. And then we have what expression? R to the raised to the power 2n over r raised to the power 2n. So this essentially two guys cancel each other out. And what do we have? Then we have the following limit. Let me, once we all understand where did this reasoning come from, we can erase it now. Let's say we erase it. We erase it, and what do we have again? We have a constant real number times a varying quantity over here. We carry this constant from under the limit sign. And is everything good over here? Well, evidently it is. In the case where r is positive and strictly larger than 1, then what do we have? In the numerator, we have a positive number plus a positive number, a positive number. In the denominator, from the number that is strictly larger than 1, we subtract 1. We get what? A strictly positive number. Positive in the numerator, positive in the denominator, overall positive argument, everything is good. When r is negative, then what happens over here? Then to a negative number, we add 1, this becomes negative, and then from a negative number, we subtract 1, another negative number. Negative number in the denominator, negative number in the numerator, comes out to positive number, everything is good again. And what is this limit? This limit again is big fat 0. And thus, what do we have here? Our limit is equal to, let's carefully write it down, 2 pi, 2 times pi, times the value of the natural logarithm evaluated at the absolute value of r. And then again, just to make sure that everyone understands, this is done under the assumption that by absolute value, r is strictly larger than 1. Let me write it down again in red so we understand what is going on. 2 times pi times log absolute value of r. Again, module absolute value of r is strictly larger than 1. This is an interesting result. And again, back in my time in the mid-80s, I do not really see how one could get a degree in theoretical physics without being, let's say, if we can somehow agree on what an average proficiency with integration is, being above average or being very well versed in computing integrals that show up in theoretical physics. And again, yes, in practice, you will virtually never compute definite Riemann integrals this way. This is just, even in the simple cases, the computations are quite involved. We will use the other theoretical tools. So as a practitioner, you will virtually never use this approach, but as a theoretician, something, for example, inside me gives me some certain aesthetic pleasure in actually evaluating integrals using this approach, using the integral sums. And here we need to do what? We need to be good at evaluating finite sums and finite products. And we need to be good at evaluating limits. And the art of computing limits is what? Is the art of dealing with inequality. So this is our wide, so to speak, theoretical tool chest of evaluating definite Riemann integrals using the integral sums. Now that we're done with both cases, when the absolute value of the real number r is greater, strictly larger than 1 and strictly smaller than 1, we will consider the case when the absolute value of r in the next couple segments is exactly 1, these cases, but this material is optional. Feel free to skip forward to the next challenge. Now that we covered the cases when the absolute value of the real number r is strictly smaller than 1 and strictly larger than 1, let us consider the case when the absolute value of the real number r is exactly 1. First, we will deal with the case when r is strictly positive, is the positive unity. In this case, our Poisson integral that depends on r, which is now plus 1, collapses into the following integral, where the integrand, the logarithmic function, has which argument now? Well, 1 minus r times 2. R is 1, 2 times the value of the trigonometric function of cosine evaluated at the argument x, plus r squared. R is 1, 1 plus 1 is 2. So now we have 2 minus 2 cosine of x, and with the integration carried out with respect to the dummy variable x. Again, we go back over here. Let me highlight it with green and carve it out here. We have this identity for the half angle. This is again nothing complicated. Our favorite middle school identity. 1 minus the trigonometric function of cosine evaluated at the argument x is twice the value of the square of the trigonometric function of sine evaluated at exactly 1/2 of the argument of the original trigonometric function of cosine. We insert this, we replace this expression, this difference, with this expression over here, and what do we have? 2 squared, because we have 2 factored out, times the square of the sine as shown over here. Again, we use the same fundamental property of the logarithmic function for any two strictly positive real numbers, a and b, the logarithm of the product this will be a, this will be b, is what is the sum of the logarithm of a and b. Represent this result over here like this. And here we have the logarithm of 2 raised to the second power. This is a constant dx over here plus, and the integral from 0 to pi of the logarithm of the square of the sine evaluated at the point x over 2 dx. In the first case, everything is straightforward. It's a triviality of itself. One of the fundamental properties of the definite Riemann integrals, integral of a constant, is that specific constant times the value of basically the length of the integration interval. In this case, it comes out to pi, 2 pi times log of 2 plus, what again? We move the square of the trigonometric function of sine down in front of the logarithm as a constant multiplicative factor here as 2 times the integral from 0 to pi of the logarithm evaluated at sine, at the value of the trigonometric function of sine, which itself is evaluated at x over 2 dx. And we rewrite this expression over here again, 2 pi logarithm, natural logarithm of 2 plus 4 integrals from 0 to pi over 2 of the logarithm, which is evaluated at, again, the value of the trigonometric function of sine evaluated at t. Now dt is the dummy integration variable. Where did this come from? Well, here we did this substitution. It was begging to be made. This is nothing extraordinary. X equals 2t. Consequently, dx equals 2 times dt. When x is 0, evidently t is 0. And when x is pi, then t is what? Pi over 2, exactly. And voila, this is what we have. This integral over here is technically, at the face of it, improper Riemann integral, this guy right here, but it can be massaged into a proper integral, x over tangent, the trigonometric function of tangent x, and it can be shown that this integral is actually, this integral exists, converges, and this integral here is associated with another name, the Swiss-born mathematician and theoretical physicist Leonhard Euler. And in order to keep the size of this episode manageable so that you guys can work through it, I will not challenge you to compute this integral using the machinery of integral sums, just like we did. This will be a separate episode. I'll do it in a separate, as a separate problem, as a separate episode, but it is possible to evaluate this here improper integral using exactly the machinery of divide and conquer, or by the book using the integral sums. I will do it to show you guys how I can do it. But here, for educational purposes, for pedagogical purposes, I will show you how Leonhard Euler evaluated this wonderful integral, and this integral will show up on this channel time and time again. Wonderful. In this segment, we will evaluate the so-called Euler's integral shown over here. And again, to keep the size of this episode manageable, I already prepackaged the result for you. So here, the first substitution to carry out is this one. T equals 2 times x over here, dt2 dx. When t is 0, x is 0. But when t is pi over 2, then x is pi over 4. So we have twice from dt equals 2 dx twice, the integral from 0 to pi over 4. I highlighted pi over 4 over here in this pinkish color so you guys understand what's going on. The logarithm then is evaluated at the argument that is sine of 2x. And we carry out this computation from here to here again. We have 2 twice the integral from 0 to pi over 4 of the natural logarithm, whose argument is now what? We unzip the double argument into 2 times sine of x times the cosine of x. Again, we split all these factors of the logarithm in 3 different terms: logarithm of 2, logarithm of sine, logarithm of cosine. Again, middle school arithmetic, nothing complicated. Twice integral from 0 to pi over 4 over constant logarithm of 2, plus 2 integrals from 0 to pi over 4 of the logarithm of the sine of x, and the trigonometric function of sine, plus 2 integrals from 0 to pi over 4 of the natural logarithm evaluated at the argument that is what? Cosine, the trigonometric function of cosine evaluated at x dx. And here is the way, pretty much, if time travel was technically possible, I would like to go back and be a fly on the wall in Euler's study room, because pretty much everything that Euler did was very witty, very clever. And this is the Euler's signature style of being witty and clever. The whole idea here is that we leave this integral as is, don't do anything to it, but with this, when this integral, we flip the variable x via pi over 2 minus z substitution, and in this case, what the cosine becomes the trigonometric function of sine. And what about the differentials and boundaries of integration? Well, dx is minus dz. When x is 0, then z is evidently pi over 2, and when x is pi over 4, z jumps over here. Pi over 2 minus pi over 4 is what? Pi over 4 minus dz. Flip the order of integration. So now what we have over here, this integral, becomes shown over here. The integral from pi over 4 to pi over 2. And again, because z is just a dummy integration variable, I flip it back. Z goes back to x, and what do we have? The logarithm of the trigonometric function of sine evaluated at x dx. But here is the cleverness and wittiness and the signature style of Leonhard Euler. Look at this. We now have one and the same integration interval from 0 to pi, broken piecemeal as a union of two subintervals, 0 to pi over 4 and from pi over 4 to pi over 2. Thus, by the property, and again, it can be shown that the integrals here converge, we merge two integrals into one over unionized intervals. And once we do that, we will have the integral of what? Exactly from 0 to pi over 2 logarithm of sine of the argument over which the integration is carried out. I apologize, here it's supposed to be t. Inertia is a bad thing sometimes. So what do we have? We put, instead of j, we put 2j. Look at this here. Pi over 2, and again, I apologize, made a small mistake over here. It will be pi over 2 logarithm of 2 plus 2 times j, plus 2 times j. And this way we have this equation over here, our original integral, j, equals to pi over 2 plus 2j. This is our final equation. This is another signature style of Euler. What do we have? A very simple linear equation in our integral. We carry this guy over, and what do we have? Minus j equals this, or j equals negative pi over times the natural logarithm of 2. So now we take this result and go put it back into the result when the absolute value of the real number r is strictly equal to positive 1. Now that we computed the value of the Euler's so-called log-sin integral, and we know that by value it is negative pi over 2 times the natural logarithm of 2, we put it back into our original expression for the Poisson integral. And what do we have here? It's the first summand, positive 2 pi, the natural logarithm of 2, plus 4 times the value of the Euler's integral, which is minus pi over 2, 4 in the numerator, 2 in the denominator, negative 2 pi. The whole thing collapses into 1, and the answer, in the case when the real number r is strictly equal to the positive 1, then again comes out to 0. Now let us quickly discuss what will the value of this integral be when the value of the real number r is strictly equal to negative 1. Wonderful. When the real number r is equal to -1, then the shape of our integrand changes slightly. From minus sign it becomes a plus sign. I showed it over here, guys, with the red chalk, and r equal to -1 because 2 times -1 becomes -2. Negative sign in front of it times -2 is +2 plus 2. And this time we will use a slightly different trigonometric identity, the one that's shown over here. This identity over here, again, nothing too complicated, going back to middle school when 1 plus cosine of x equals twice the square of the cosine evaluated at half the argument of the original trigonometric function of cosine. Then if we go through the same maneuvers, we'll obtain the same result. 2 times pi times the natural logarithm of 2 plus 4 copies of the integral from 0 to pi over 2. But this time the logarithm is evaluated at the value of the trigonometric function of cosine, shown in red. So we go back to this integral. This integral is related to the Euler's log sin integral, whose value we just computed. And here we do what? We do the substitution x equals pi over 2 minus t, because then what happens? Dx equals minus dt. When x is 0, t is evidently pi over 2. When x is pi over 2, then t is what? Pi over 2 equals pi over 2 minus t. T is 0. And our trigonometric function of cosine becomes the trigonometric function of sine. So now with this substitution we flip our integral into the integral from 0 to pi over 2 of the natural logarithm evaluated at the sine of x dx. We already know the results. It is negative pi over 2 times the natural logarithm of 2. We inject this result back to over here. This is the guy. And we obtain the value again. 4 times negative pi over 2 comes out to negative 2 pi natural logarithm of 2 plus positive 2 pi natural logarithm of 2, 0 over here and 0 over here. So now we covered all the cases when the absolute value of the real number r is strictly less than 1, when it's strictly larger, greater than 1, when it is equal to precisely positive 1 and negative 1. Wonderful. And as such, as a short executive summary, the value of the definite Riemann integral that is usually associated with the name of the French mathematician Simeon Poisson, which runs from 0 to pi of the natural logarithm evaluated at which point? 1 minus 2 times r times the value of the trigonometric function of cosine evaluated at x plus r squared, with the integration carried out over dx. We now exhausted all the cases. That integral is equal to 0 if the absolute value of the real number r is less than or equal to 1. Remember that when r is equal to +1 or -1, this integral vanishes again. And if the value of the absolute value of the real number r is strictly larger than 1, then the value of this here Poisson integral is given by this expression: 2 times pi times the natural logarithm of the absolute value of r. And if we go back from our topological or metric spaces perspective, when the real number r can be interpreted as the distance from the origin to the point r that roams the upper half plane, the case when this integral is 0 corresponds to what? Corresponds to the case when the number r roams the entire origin-centered unit half disk that lives in the upper half plane. So that includes all these cases over here. The entire half disk is shown over here, delivers the value of 0 and the boundary too. So evidently on the boundary of our origin-centered unit half disk, the value of this integral is 0, and only when the point r jumps outside and goes somewhere over here or over here, then we get this non-zero value. And again, now you guys know how to evaluate certain definite Riemann integrals using the integral sums approach. In sometime in near future, I will also show you how can I evaluate the famous Euler's log-sin integral using precisely the integral sums approach. But for now, we're done with the mathematical problem S2M45, and we will move on to a new challenge next. With this episode, we conclude the dedicated study of the divide and conquer problem solving approach, but that doesn't mean that you should forget all about it. On the contrary, every time you come across an interesting problem, try to see if you can dovetail your knowledge of how the divide and conquer problem solving approach works into the process of generating a solution for your problem. But we will move on, and starting with the next episode, which I will entitle Evaporating Watermelons, we'll begin a dedicated study of the so-called invariant problem-solving approach. This is a hint, but the problem statement here for the math problem S2M46 is the following. 100 tons of watermelons are loaded onto a ship for transportation to the farm market where the watermelons will be sold at the point B. At the point A, the members, let's say, of FDA, Food and Drug Administration, stick the needle into each and every watermelon, and they determine that one watermelon contains 99% water or moisture. During the transition, while the ship with 100 tons of watermelons sails from point A to point B to the farm market at the point B, some amount of water or some amount of moisture evaporates. When the watermelons arrive at the point B several days later, let's say, the members of the FDA, Food and Drug Administration, stick the needles into watermelons, and lo and behold, they determine that each watermelon now contains 98% water at the point B. And the question is now, how much do the watermelons weigh now at the point B? In other words, to be perfectly clear, 99% water content in the watermelons at the point A, several days transition down the river to the farm market from the town A to town B. Some moisture or some water from the watermelons evaporates, lost due to evaporation. And at the point B, the water content of each watermelon is 98%. How much do the watermelons weigh now at the point B? This is it for this episode. Thank you very much for watching. Thank you for your time. I will see you in the next episode, in which I will explain how the invariant problem-solving approach works, and in which I will share my solution of the mathematical problem S2M46.